All right, so let us start. So it's my pleasure to introduce Carlos Arreche, and he'll speak about differential transcendence of elliptic hypergeometric functions through Galois theory.
Okay, thank you to the organizers for inviting me to speak here. Let me also thank the NSF for partially funding this work and also my travel here. This is joint work with Thomas Dreyfus and Julien Roques. My aim is to explain things as clearly as I can. So I want to have something a little bit for the experts and something also for either grad students who happen to be here or people who are not experts in the parts of differential algebra that I work in. So of course there's a risk that in trying to please everyone, I'll please no one, but hopefully that won't be the case today. Most people here know what differential transcendence is. Most people have some notion of what the Galois theories that come up here are. So I'll explain that anyway, just in case. And I suspect that you've never heard of elliptic hypergeometric functions before. So I want to start by telling you as best I can why people care about these functions. That will be very brief because it has to do with mathematical physics, and that's just not my jam. But then also try to tell you explicitly what they are. So I'll begin telling you these functions were introduced in the early 2000s in the mathematical physics community by Spiridonov, and they are simultaneously analogs and generalizations of the classical Euler-Gauss hypergeometric functions, but somehow built out of elliptic curves. Okay, so I'll make this more precise a little bit later. The reason people care about these things are listed in here. If you have any questions about their applications in representation theory, four-dimensional supersymmetric quantum field theories, and the other two things, you'll have to ask them. I would like to know more, and I don't. In fact, when we put our paper on the archive, this community got wind of our work and invited us to come talk about it at a workshop on mathematical physics, which gave me some appreciation for what our evolutionary ancestors went through, because I really felt like a fish out of the water. But they were really kind and still willing to listen. So go meet physicists; they're cool. So this is why they care about them. Somehow they come up in a very natural way in some models that they study. What we proved about them is that, in a sense that I'll make precise later, most of these functions don't satisfy any algebraic differential equations with elliptic function coefficients, and a result was obtained as an application of a new algorithmic criterion that we proved in the context of the differential Galois theory for difference equations, which is a special case of the theory developed by Hardouin and Singer in the case of elliptic curves. Okay, so in recent years, in work of Dreyfus, Hardouin, Roques, and Singer, they apply this theory to say things about the generating functions for walks in the quarter plane, and this is another kind of application of this theory to a similar kind of result in some sense. So let me tell you what these functions are. So I'll first start by defining theta functions. They are related to the so-called Jacobi theta functions that you might be more familiar with, but they're not exactly the same. They're modified a little bit. So I don't want to tell you how these are related to those explicitly. So here's what they are. You first define this infinite product like that, the ZP infinity, and then you use it to define this function that's going to end up being holomorphic on the punctured complex plane. And the two things that I want to point out about this function is that, first of all, because of its explicit description, I can tell immediately that its zeros are exactly the integral powers of this number p. And I'll keep using this notation. P to the z is going to denote the set of integer powers of that p. Moreover, one can check, it's not immediately obvious, but it only takes a little bit of work, that this theta function satisfies the functional equation that I have down at the bottom. Okay, so so these theta functions have been modified from the original Jacobi theta function in order to make the functional equation look a little bit nicer and cleaner. Okay, usually you get some messy thing involving the p. So I'm going to use theta functions to describe elliptic functions. That wasn't really our choice exactly. The physicists expressed all their work about elliptic hypergeometric functions in terms of theta functions in the first place. Also, eventually, we need to use an earlier result of Dreyfus and Roques that also happens to want to express elliptic functions in terms of theta functions. So we were just happy that we could meet in the middle there. So I'm going to be using the multiplicative model for an elliptic curve. This is roughly familiar to most people, but not exactly familiar to most people. So you're probably more used to thinking of an elliptic curve as the quotient of the complex plane by a lattice. So if you want to go back and forth between these two models, here's the dictionary, as it were. If you exponentiate, like 2 pi I w being your variable in the complex plane, then that relates the two quotient groups that you have in there. Okay, so given 2m different non-zero complex numbers, if I ask for this balancing condition that the product of the first m of them is equal to the product of the second m of them, I can write down this function on the right, f of z being any non-zero constant multiple of that product of theta functions above and below. The simple functional equation satisfied by my modified theta function is going to force any quotient like this to be an elliptic function with respect to multiplication by p. Not only that, but in fact, any non-zero elliptic function can be written in this way for some appropriate choice of numbers, a's and b's, satisfying this balancing condition. So throughout the talk, there are going to be a few more equations called a balancing condition, and every single time, the role of the balancing condition is going to be to force a certain thing that I want to write down to actually be an elliptic function. The last thing I want to point out, one convenience of writing elliptic functions as a quotient of products of theta functions in this way is that you can read off the divisor of the elliptic function on the curve immediately from this expression. Okay, so we'll want to be able to have that theoretical knowledge later on. Any questions so far? Okay, so before I tell you what the elliptic hypergeometric functions are, I need to tell you about the elliptic version of the gamma function. This was introduced by this person, Riesenars. So first you define a similar infinite product as the one used to define the theta function, but now it has a p and a q in it, and it's quite analogous. And this elliptic gamma function is defined by this expression. So when I went to Sweden to talk to the mathematical physicists, as I start going through the slides, I say suddenly right here, it's like I'm suddenly realizing that I don't know the history of these objects very well, and I'm quietly terrified that the person who invented these functions is probably in the audience, and he was. Said it was me. So too late, but now here's the person. Very nice guy too. Okay, so the gamma function satisfies this pair of functional equations. You can tell immediately that its definition is symmetric in P and Q, and if you squint and stand really far away, this looks a little bit like asking for the shift of gamma to give you a factor of the variable outside. Here, the two different thetas are playing the role of that x that comes out when you look at gamma of x plus 1. So I'll show you in the next slide how these elliptic gamma functions come up in defining what are called the elliptic hypergeometric functions. That formula is going to be an elliptic analog of the so-called Barnes integral formula for the classical hypergeometric functions. I want to write it down because I think I'm going to have extra time at the end. So why not? Okay. So this 2f1, depending on two parameters b and c that are symmetric, and then c over here, function of one variable, you can express the Euler-Gauss hypergeometric function via this formula. You can also write it down as a series and in a bunch of different ways, but it's this expression for them that's going to be kind of directly generalized by the formula on the next page. So that story goes like so. I give you 8 complex parameters, epsilon 1 through epsilon 8, and I ask for them to satisfy this other balancing condition. Is a little different from the one that I had before, but again, the role of this is eventually going to be to force a certain thing to actually be an elliptic function. So it's going to be a function of a complex variable z, depending on the parameters epsilon, and it's defined. Well, what do? You first define some other version of what they call an elliptic hypergeometric function that depends, more or less symmetrically on 8 parameters t1 through t8, and that's just what it is. And then from the parameters t1 through t8, you can do a change of variables that turns it into a function in z, depending on some other parameters epsilon. Okay, so there's the reparametrization is explicit, and I don't want to show it to you. And if you ask me to show it to you, I can, but I don't want to. Okay, no one. Great, thank you very much. It's not too messy. It's just really difficult to parse. I do want to mention a few things about it because the version of our result that I'm going to state is not exactly true as stated. Okay, and it has to do exactly with this parametrization. I don't want to get into exactly what the issue is. There's a little subtle thing, but I can point out now, without having shown you what the reparametrization is, that I'm starting from 8 parameters, getting 9. What gives? Okay, so it has to do with trying to get too many things out of too few. They have to be related already, and our condition that's going to force the elliptic hypergeometric functions to be differentially transcendental is precisely a condition on the parameters epsilon being kind of independent. Okay? So that's not true on the nose because of this reparameterization, and we have a more precise result that takes that into account. I don't want to get into it, but still the version that I'm going to write down, even though it's not literally true, still gives you a flavor for what we did show. So this function that you obtain after doing that thing that I did not show you, it happens to satisfy second order linear difference equation over the field of meromorphic functions on the elliptic curve that you get by quotienting out C star by the integral powers of P. Okay. I'll actually show it to you explicitly later, but for now, just to tell you that this was our entry point into mathematical physics. So, okay, so never mind what the functions mean, where they converge. I don't know these things, but if you give me a linear difference equation over an elliptic curve, I can put in the machine and turn the crank and see what comes out. Okay, so here's the embarrassing slide that clearly I had meant for someone else, but now I have to discuss it with you. If you're not too familiar with how to use Galois theory after you took it in your algebra class, if you only take away one thing from it, it should be this: Galois theory allows you to deduce facts about solutions to certain kinds of equations by applying results from group theory. Whatever the groups happen to come up in your Galois theory, if you know enough about them, you can then abuse of that technology to deduce new facts about solutions of things that you care about. In particular, the kind of application that's going to come up in our main results is that we want to conclude that certain things are differentially transcendental, as in they satisfy very few relations, and that's going to be equivalent to the corresponding Galois group being large enough. Okay, so the algorithmic conditions that I'm going to write down soon are going to be conditions that force the Galois group to not be too small. To use a Galois theory, I need to specify what my base field is. In this case, again, going to take the field of elliptic functions with respect to P. That's the meromorphic functions on the elliptic curve C star mod PZ. And then I want to endow this field with an automorphism, a difference operator. And I'm going to get it by shifting everything by some other point on the curve that I'm denoting by Q. This condition that P and Q don't have any non-trivial powers in common is equivalent to asking for the corresponding point on the elliptic curve to be non-torsion. Because some people get confused when you have an automorphism of finite order. That some people might just be me, but in any case, here's the condition that we use in the Galois theory. So my field is endowed with this difference operator, and then there's an invariant derivation on the field of meromorphic functions over an elliptic curve, which in this case, because of the model that I chose, actually has this explicit form that one can write down. And well, here you can just check using the chain rule, but in general, regardless of which model you pick to talk about your elliptic curve, you're going to have that the derivation and the automorphism commute with each other. So when you're given a field like that, endowed with an automorphism and a derivation that commute, you can start doing Galois theory. You impose this technical condition on the ground field just to make things nicer. I don't want to dwell on it too much, but if you're not too familiar with what this means, let me tell you why you don't need to worry. I'm trying to conclude that certain things are differentially transcendental over some small field of meromorphic functions. So if I enlarge the field and then prove differential transcendence over a big field, surely I have it also over a small field. Okay, so for today, you don't need to worry about this. I'm just trying not to lie to you. Okay, so you start from a linear difference equation, like so. The condition that the first coefficient and the last are non-zero, are just meant to make it so that it's not secretly a lower order equation. And then it turns out that just as in classical Galois theory, you can form some kind of analog of a splitting field for the equation. Here, the true story is a little bit more technical, but you roughly get it by adjoining as many solutions to the equation as you could possibly have, and then throwing in all of their sigma and delta iterates. Okay, so this is going to be a sigma delta ring extension of the ground field. I'm omitting something because my slide got too busy. If you're familiar with this, what I'm not saying is that I should also throw in the inverse of the determinant of the Cassoratian matrix. Okay. It's a condition that guarantees linear independence. But roughly speaking, you take K and you adjoin to it as many solutions to the equation as you could possibly have, and then you close it under sigma and delta. So now this K algebra is going to have an abstract group of automorphisms that commute both with the sigma structure and the delta structure. So a priori, this is how come the group is able to measure the kinds of differential equations that the solutions are allowed to satisfy. If morally speaking, if they're highly differentially related to each other, then that's going to force the group to be smaller, because when you apply an abstract an abstract linear transformation to the vector space of solutions, you don't expect in general that the new things are going to still satisfy the same polynomial equations. Okay, so polynomial relations among the solutions cut down what the Galois group should be, and I already suggested this in the roundabout way that I chose to say it. But it turns out that this abstract group of automorphisms of R over the base field K, it has a structure of a linear differential algebraic group. So let me tell you a little bit about what those are. These are the analogs in differential algebra of the linear algebraic groups in non-differential algebra. There are different ways to say what these things are. For me today, they're just going to be subgroups of GLN over some differential field C that are defined by polynomial differential equations in the matrix entries. So I have a few the first examples of this kind of object. First of all, algebraic groups, linear algebraic groups are also linear differential algebraic groups, because polynomial equations are very special kinds of differential equations where the derivation happens to not show up. A little bit more interesting, if I give you a linear a linear algebraic group over what's called a subfield of constants, so the things that have delta of them being 0, that's now going to be a linear differential algebraic group, because it's defined by the same polynomial equations defining the algebraic group, together with one more equation for each matrix entry that says that delta of that is 0. More interesting examples are given by the subgroups of here GA denotes the additive group of the field, and GM is GL1, just a multiplicative group. If I write down a linear differential operator and I ask for all the things that evaluate to 0 under that, that's going to be closed under addition. So voila, there's a subgroup that's defined by a differential equation. And down here, well, similarly, because this logarithmic derivative can show that it takes products into sums. If I demand that the d log of something satisfy a linear differential equation, that's going to cut out a subgroup of the multiplicative group that's defined by some polynomial differential equations when I'm done unraveling this. Okay, so there's less known about linear differential algebraic groups than about their non-differential counterparts. But still, we do have a lot of results that we can apply in this theory by knowing enough about linear differential algebraic groups, so what's true about them and how they work. You can actually deduce concrete facts in examples using these theories. So one of these classification results is due to Cassidy, who classified all the linear differential algebraic subgroups of GA and GM, and they all have this form that I wrote down above. Okay, so these aren't just examples. At least over here, they are all the examples. Okay, so let me tell you about the algorithmic result that we proved in the context of this differential Galois theory for difference equations. I say here, this isn't just a result about the elliptic case, but actually applies uniformly under what I'm calling mild conditions on the otherwise arbitrary sigma delta field K. For the experts, let me tell you what those are, because they show up all the time. Is this condition P? First I need for K to not have any finite algebraic extensions that are also sigma extensions, and also I want K to be C1 field. Okay. These conditions are familiar to people because they really come up all the time when you're trying to apply certain structural results in just algebraic difference Galois theory. Any questions about that? Oh, I didn't say what a C1 field is. Yes, the base field K needs to be a C1 field, and I also ask for K not to have any finite extensions to which you can extend sigma. So in the Q case, for example, right, I can't work over the rational functions because I could extend that to any, like I join the nth root of x kind of thing. In the elliptic case, we similarly have to worry about all the curves that map down to the original one by an n power map. Okay, but for this kind of application, what do I want to say? The first thing about there not being any difference finite algebraic extensions, that can be fixed by just throwing in all of them. Then again, if I'm trying to prove results about differential transcendence over a small field, I don't care about enlarging the field to prove that then. So in the cases that actually show up, that I've seen, people care about the shift, Q difference, Mahler, and elliptic case, and in all those cases you can work over a base field that satisfies these mild conditions. I don't know if there are any other examples, but in the ones that come up in practice, this is always satisfied, the conditions that I didn't write down. So what are our conditions? I give you a second order linear difference equation. And it's enough to make sure that, first of all, there are no solutions to this second order nonlinear, first order nonlinear difference equation. This is called a Riccati equation, and like in a bunch of different similar theories, this condition on on this U belonging to K is exactly what you need in order for the underlying difference operator to factor over the ground field that you have already. So I ask for there to not be any solutions to that Riccati equation, that is for the operator to not factor over K. And then the second condition is for there to not exist a telescoper, which when I hit the d log of b with it, that I get sigma h minus h for some h in the base. This condition and its analogs are also familiar from people doing all kinds of similar Galois theories, because they come up in trying to control what the image of the determinant map on the Galois group is going to be in the end. So these things show up all the time for people who are familiar with this. What's a little bit surprising maybe is that it's enough to ask for just those two things, and if the answer is negative in both cases, then I can guarantee that any non-zero solution to my linear difference equation is going to have to be differentially transcendental. So this is the result that we apply in the particular case of the difference equation satisfied by the elliptic hypergeometric functions, but it holds in general. asterisk in general. Okay, so I mentioned earlier that Spiridonov had shown that the elliptic hypergeometric functions satisfy a second-order linear difference equation. I've written down what the equation is. So it's written a little bit weirdly. You only have sigma of y, sigma inverse of y, and y. But after applying sigma, this is a second-order linear difference equation. And the coefficients. There are three kinds of coefficients in here: a of z inverse, and this nu. Nu, when you look at it at its expression, you see that there are no variables in it, so it's just a really funny complex number. It's just a constant. And a, well, here's what a is. Why that a? What does it mean? Again, I can't. I don't know. I wish I knew. I don't know. If you know, tell me later. But what I can tell you about it is two things. You actually can sit down and show from this expression that it does have to define an elliptic function. Okay, you use the functional equation, and where you have the z squares, you have to kind of like do it twice. But the balancing condition that I had, that I wanted the product of the parameters epsilon to be equal to p squared q squared, is exactly what's needed to force this a of z to actually be an elliptic function. Not only that, but because I've expressed it as quotient of power products of theta functions, I can write down its divisor explicitly, and this knowledge will be crucial later. Okay, so how did we show? How did we apply our algorithmic criterion to these funny functions? In the first slide, I told you that we showed that most of these functions are differentially and transcendental. Here's what I mean by most. So I know that the parameters epsilon have to satisfy this balancing condition, and we said suppose that that's essentially the only multiplicative relation among the parameters and p and q. In the sense that the map from Z10 to the multiplicative group given by putting those things as exponents into the epsilons and p and q, the kernel is exactly this relation. Okay, this is what I mean by induced from the balancing condition. Assuming that independence, I have to show two different things to conclude differential transcendence from our criterion. For the first one, to show that there isn't a solution to the Riccati equation, we actually applied earlier work of Dreyfus and Roques, where they develop an algorithm similar to the Hendrix algorithm in the other difference cases, or the Roques algorithm in the Mahler case, or the Kovacic algorithm in the differential case. They have something like that for difference equations over elliptic curves, not worrying about differential anything at all, just trying to compute the algebraic difference Galois group. And the condition that they give to decide existence or non-existence of solutions in the ground field to the Riccati equation are exactly expressed in terms of the divisors of the coefficients a and b that came from the equation, and our independence condition basically guarantees that these conditions that they have can't be met. Because the things have to be independent, you can't fulfill all four different things that they list that a solution to Riccati would have to satisfy. So it's a contradiction proof. And then for the second thing about there not existing a telescoper for the d log of b, we also do an ad hoc argument. For me, it's ad hoc, but maybe it's part of a method that other people understand better. But also from knowing the divisor of b, you can deduce that you can't have a telescoper. Also as a consequence of the independence condition. So I'd like to, towards the end, tell you a little bit about the proof of our main result that we applied in the specific case of the elliptic hypergeometric functions. this algorithmic criterion. So it's not a priori that there are three main possibilities for what the Galois group of any second order linear difference equation might be. First, it's going to be reducible, that is, if you like, conjugate to an upper triangular group exactly when you can factor the operator or exactly when you can solve the Riccati equation. So our first condition says that we're not in that first case. Then it might happen that G is irreducible and imprimitive. That's this kind of like dihedral thing that happens in the second case. Or if not, then G has to be large enough to contain SL2 of the differential constants. Okay. So we're not in case 1. Maybe we are in case 2 or 3. We don't know. But in any case, show that the non-existence of a telescoper for the D-log of B, that's ends up being equivalent through the Galois correspondence to showing that the image of the determinant on G has to be the full multiplicative group Gm, which is too big. And so from that, we have some arguments that allow us to conclude that any one solution has to be differentially transcendental already. This doesn't say, if I take two linearly independent solutions, they might satisfy some polynomial differential relations into variables. We don't know if that happens or not. We don't address that question. But any one non-zero solution has to be individually differentially transcendental. So that's how that went. Then let me make a few remarks at the end. As I mentioned before, our algorithmic criterion works uniformly in all these other cases of interest that people have worked on. This kind of thing at the end, insert your problem here. It's like I have this hammer and I'm looking for nails. If you have a nail, please tell me about it so I can smack it. So you can only apply your criterion if you can verify the two things that are in it. So to verify the first condition of non-existence of solutions to the Riccati equation, there are algorithms by Hendricks in the shift and Q dilation case, by Roques in the Mahler case, and by Dreyfus and Roques in the elliptic case. In the elliptic case, you do have to know what the divisors of the coefficients of the equation are. Okay, so if you don't know how to do that, then right now you wouldn't know how to apply the first step of the criteria. And then it's something that people have been discovering in a bunch of different cases. I hope I don't annoy people who are experts on this, but the kind of telescoper relation that I wrote down for the D-log of B, in most cases, it's really difficult to satisfy. Okay, so there are a bunch of results in specific cases that basically say if there is one, then it has to be really simple, and you can rule that out easily. I'm not aware in the elliptic case of results that are that strong, but maybe there are results like that that I'm just not aware of. The last thing is that there are a bunch of different algorithms to compute different kinds of Galois groups for different kinds of second order linear operator equations. As of today, there isn't a complete algorithm to compute the differential Galois group for a second order difference equation in the Q case, nor in the Mahler case, nor in the elliptic case. For those equations, now we have a result that uniformly allows you sometimes to conclude that the solutions, any one solution, has to be differentially transcendental. Even in the shift case, there is such an algorithm that I wrote down. But even then, if you wanted to get the answer that we provide here, you'd have to compute the whole Galois group, and then from that knowledge, deduce this fact about the solution. Okay, so this gives you a shortcut. If all you want to conclude is that any one solution has to be differentially transcendental, you should do this and not what I said earlier in that other algorithm. Okay. So I think that's all I have. Thank you for your attention.
any questions?
So I was wondering if you consider an elliptic hypergeometric function for some p, and you choose a p prime because this is multiplicatively independent from p. And you take another hypergeometric function versus p prime. Are there some known results about algebraic independence of these two functions?
This is a very nice question. I hadn't thought about it. So the quick answer is I don't know, but it might be that the math physicists did think about this when they were doing their thing. I think it's a very natural question. I don't know.
And another one which is related to this differential transcendence criteria, so people try first to show that, for instance, there are no holonomic function unless it's in the base field. So do they have some result for you take an elliptic equation and then it can the function either it's in the base field or it's not holonomic. I mean, there are no.
I think I'm not too familiar. I have my understanding is that there are some recent results in this direction. I think that some of them due to you and other people, but no, I see. I would look. I have some religious beliefs about this. I imagine that something like that is true in this kind of setting, but I'm not sure. Perhaps I don't know if someone wants to jump in.
Do you know whether SL2 of the constants can occur as a Galois?
I don't know. Again, this is part of my religion. I think no, but right. So Shefke and Singer have a really cool results for compatible systems of differential and difference equations that applies in the shift, Q, and Malloy cases, and that generalizes a bunch of other cool results. So the result of Shefke-Singer implies in particular that in the shift, Q, and Malloy case, you can't have SL2 of the constants actually showing up as a Galois group. In the elliptic case, this is just part of my credo, but it's not a fact. So I think that the same conclusion is true, and one would ideally need some elliptic version of Shefke-Singer, and we'll see what happens with that. If you want to work on this, don't. Please give me a couple months, or call me.
A year ago, I saw Michael give a talk on something related to this, and he had some weird hypothesis about homological. It was like homological dimension 1 or something.
That's what a C1 is.
That's what it was. Yeah, it's in the same. That's where it's coming in, right?
Yeah.
So it's the same.
Yeah.
No, I just was wondering if it's that. It's your work.
Yes. Yes, it's that.
It's a general phenomenon in this Galois theory. It's to ensure that you only have trivial torsions.
Yeah. And right. So I can maybe make a comment about what the role of this condition is. I think and I hope over a C1 field, you can always find a gauge transformation that puts the linear difference system. You get a matrix difference equation, and you can always force the matrix to be a k point of the Galois group itself. Which is a different way of saying that you don't have triple torsors, and this ends up being a really useful used by Hendricks and in the shift and Q case, and by Roques, and presumably also by Dreyfus and Roques in the elliptic case, to make these algorithms run.
Any other questions? If not, let us thank.
So, as the last speaker, it falls on me to thank our amazing team of fearless organizers. I've been to a number of darts, and they're always great. This was a really good one, not comparing to the other one. So, gosh, I'm going to get in trouble. And it takes a lot of work to put something like this together. And please, let's give a hand to our organizers. They were amazing. 10 more darts.